All right, we're going to talk about nomenclature today. So this is naming compounds. So a lot of people have a lot of confusion with this. This is kind of what the dihydrogen monoxide video was about. So let's talk about this. I will say that we got lucky. People in this class usually, most of us got lucky because the language for chemistry is English. So if you want to talk chemistry with somebody who speaks another language, you can. You might not be able to eat lunch with them and order with them, but you can definitely say something like sodium hypochlorite, and they'll know exactly what you're saying, even if they speak no other type of English. Alrighty, so what we need to be able to do is name compounds. And one of the problems with that is you have to identify the type of compound you're looking at before you can actually name it. So before I can say something like sodium hypochlorite, I have to look at that substance and realize that substance is an ionic substance. Okay, so how do I get that ionic out of that? So I need to talk about ionics and covalents and acids. An ionic compound is something that is a compound formed between ions. So a positive ion, a cation, and a negative anion, an anion. And those are usually a combination of a metal and a non-metal, like sodium hypochlorite. Sodium is a metal and hypochlorite is a polyatomic ion. So two ions. Covalent compound would be something that's composed of just non-metals. So like water, H2O, hydrogen is a non-metal, oxygen is a non-metal. Carbon dioxide, two non-metals, carbons and oxygen. Carbon monoxide, two non-metals. So those are named covalently. All right, so then acids, for the most part, acids are easy to identify because the substance starts with an H. There is one exception to that, one common exception, but for the rest of the time, we're going to be talking, when you're going to name an acid, you're going to look at it. If it starts with an H, you will name it as an acid, not as an ionic or covalent substance, but as an acid. There are other nomenclatures like organic and biochemistry, but we're not going to talk about those in this class. That would be for other classes. So how do I identify something as ionic or covalent? All right, so use ionic naming if the molecule contains a metal or a polyatomic ion. So my first compound here is LiBr, lithium bromide. How do I know that this is an ionic compound? It's an ionic compound because lithium is a metal. So I know I don't have to look any further. This is an ionic compound because lithium is there. How do I know the next one is also an ionic compound? Because NH4 is one of the polyatomic ions that I've got on my polyatomic ion list. So if it's got a polyatomic ion in it, that means that is an ionic compound. And the last one's pretty easy. There's a metal, calcium, and there's a polyatomic ion. So this one's absolutely ionic because it's got both requirements or both instances, which would be a metal and a polyatomic ion. Okay, so when you look at a formula, you're going to look and, hey, is there a metal there? Or is there one of those polyatomic ions? That's what you're going to do. And if it is, then you have to say, okay, that's an ionic substance. I'm going to name it as a covalent compound if there are no metals or polyatomic ions, like CCl4. That's carbon and 4 chlorines, no metals, no polyatomic ions. SO2, that's sulfur and oxygen, both nonmetals. So that's no metal, no polyatomic ion. So I would name those as covalent. And again, if I'm doing an acid, it starts with an H. So here's hydrochloric acid, starts with an H. Here's sulfuric acid, starts with an H. The exception to that is the acetic acid. You can see acetic acid written CH3COOH. And there's the H that makes it an acid. So how are you supposed to know that this is an H? Well, because you know that CH3COO is acetate. And when I attach an H to a polyatomic ion to make it become zero charge, so I'm going to take away this negative charge because a hydrogen is going to show up with a +1 charge. And now what I've done is I've added an H to a polyatomic ion to turn it into a molecule, meaning cancel out its charge. And so this has to be an acid because what did I do? I added an H to it. That's what makes it an acid. So if I look at NO3, that's nitrate. If I add an H to it, it's HNO3. And the H came as a plus charge, canceling out the nitrate's minus charge, and that's nitric acid. So I'm looking for H's that have been added to polyatomic ions. So let's go over the ionic naming. There's a couple of options we have to talk about with that. So first, I'm gonna erase all this stuff. Alrighty, so the substance gets named for its metal, and then it's going to get named for which will be the cation, the positively charged part, and then the anion is always going to have its name truncated and have a suffix placed on it of IDE. So NaCl, this is sodium. It's not sodium chlorine. It's sodium chloride. So that's what I mean by this IDE ending. We'll always be doing that. So what do I do over here? Okay, I've got, in this case, I've got to name this for what's here. And what is here is a calcium. Okay, so calcium. And what's the other thing? Chloride. And I'm able to name this just as is because calcium is in column 2. It has one possible oxidation state, which is +2. So I don't have to tell the person what its oxidation state is. I can just assume that they know what that is. So there's calcium chloride. What you should notice is it doesn't say calcium dichloride. That's not a part of the ionic nomenclature system. So the next one is aluminum and oxide. And again, I don't say dialuminum trioxide because that's not how ionic nomenclature works. I just say the name of the metal and then I say the name of the non-metal with an IDE ending. So the next one is strontium. What is that about? Strontium sulfide. Okay. And then my last one here is barium bromide. That's it. Okay, so I got these negative charges with these IDEs ending. And the reason that this was pretty easy is because barium, strontium, aluminum, and calcium only have one oxidation state. They can only have one possible plus charge. The calcium and the strontium and the barium are all +2, and then the aluminum is a +3. Okay, so now I'm going to make it a little harder. Just made it harder on myself, actually. I have the eraser picked. Alrighty, so, oh, you know what? That's dumb. I shouldn't have done that. What I should do is, and I'm going to do it this way. This makes more sense. So I'm going to go backwards now. I'm going to delete this. So now I've got calcium chloride, and I want to know what the formula for that is. So what I need to do to write the formula is I need to look and find calcium on the table and realize, okay, calcium is a +2 charge and chlorides are a -2 charge. So how do I put those together? I have one calcium and I have 2 chlorides. And so that's how I go from my name to my formula. So if I look on the table, I can see that aluminum has a +3 charge. Oxygen has a -2 charge. So if we play least common multiple, that would be 6. So I need a +6 and a -6. So I can get +6 by having 2 aluminums, +3 and +3. And I can get a -6 by having 3 oxygens, -2, -2, -2. And then it cancels out. Strontium is in that second column. It's a plus charge. There are no exceptions to that. And sulfide's in the oxygen column, so it's going to be a -2 charge. So this is just SRS, strontium sulfide. And then barium is also in that second column, so it's got a +2 charge. Bromine's in the chlorine halogen column, so that's a -1 charge. So I'm going to need 1 barium, and I'm going to need 2 bromines. So that's how I go about naming those. And everybody has to end up with a 0 charge, which is why I've got 2 calciums to 1 chlorine and 3 oxygens to 2 aluminums, and so on. Okay, so these guys are simple. What we're going to have to deal with now is, let's go and do copy, delete, make this bigger. I'm going to put this down here just for a sec. Okay. All right, so let's say I've got the formula and I want to come up with a name for this substance. Okay, so what I have here is iron and bromine. So that's a problem for me because iron's a transition metal with more than one oxidation state. So I can't determine what the oxygen or what the charge oxidation number on the iron is until I look at what it's connected to. The bromines have a charge of -1. There are 2 bromines there. So -1 gives me a -2. So iron must have a charge of +2. So great, my iron has a charge of +2. So the way I'm going to tell the person about this is I'm going to say iron with a +2 charge bromide. So we're going to do that same thing with the next one. So bromine again has a -1 charge, but now it's 3 bromine. So -1, -1, -1. So I'm going to need a +3 on my iron. So now I have a different substance, iron 1, 2, 3, bromide. You have to do this. And we didn't have to do this with the other substances because the metals only had 1 oxidation state. But now iron has actually more than 2, it has 3 oxidation states. We're just showing 2 of them here. These are different substances. If you try to do a chemical reaction with iron 2 bromide, but you needed iron 3 bromide, you wouldn't get the reaction that you wanted. So you're going to need to tell the person which, if someone said, I'm going to use iron bromide, my response would be, which one, iron 2 or iron 3? So that's why you need to tell me iron 2 or iron 3. Okay, so sulfur is in the oxygen column, so its charge is a -2. So that's -2, -2, -2, because there are 3 sulfurs here, so that's -6. So I need a chromium to get up to +6. There are 2 of them though. So if each chromium has a +3 charge, then that gets me to +6. So again, least common multiple. So I'm going to say chromium 3 sulfide. Okay. The next one, the oxygen's charge is a -2. And so -2 -2 is -4. And so then my lead's charge has to be, in this case, a +4. Okay. So then I'm going to say lead 4 oxide. If you don't know how to write Roman numerals, you're going to need to a little bit here. So there's 1, 2, 3. I wish that this was 4, but that's not 4. Sorry. This is 4. Okay, let me do this. This is 5. Okay, and so the way they write the way that the Romans wrote their numbers is they said 5 - 1. So if I write the smaller number in front of the larger number, that means I'm subtracting it. So 1, 2, 3, 4, 5. And so then 6 would be V1. That's a 6. V2 is a 7. V3 is an 8. And then X is 10. With a 1 in front of it means 9. And then X is 10. All right. So the reason we're not using Roman numerals is because they're terrible. And so instead of using Roman numerals, we're using these Arabic numbers. Much, much better. There is a silly meme floating around the internet talking about, oh my goodness, I can't believe they're teaching our children Arabic numbers. It's just like a way to incite people to get them mad. These Arabic. These are the Arabic numbers. And thank goodness they came up with those. Otherwise, we'd be using these terrible Roman numerals. But sorry, in chemistry, we use Roman numerals to describe charges within variable oxidation state metals. Okay, so let's go the other direction with this. Where's my cursor? Okay, Mr. Cursor, come on down here. So now I've got these substances and I want to, these names, and I want to go to the substances. So the nice thing about this is I'm being told you have a +2 charge. And then I need to look up that bromine's got a -1 charge. So then this is going to be Fe. And then I'm going to need 2 bromines to cancel those out. Okay. This is telling me that the iron has a +3 charge and the bromine still has a -1 charge. So Fe, and in this case, I'm going to need 3 bromines. Okay. This one is telling me that I've got a +3 charge and my sulfur is in my oxygen column. So that's a -2 charge. So least common multiple is 6. So that means I'm going to need 2 chromiums and I'm going to need 3 sulfurs. 3 sulfurs to cancel that out. And I'm being told that this is a lead with a +4 charge. So I got my lead, got my lead. Oh my goodness. I've got my lead, and that guy's got a +4 charge, and I've got these oxygens, each with a -2 charge. So I'm going to need 2 of those. -2, -2 gets to me to a +4 charge. Okay. How do I deal with it with polyatomic ions? It's pretty easy. The polyatomic ions names never change. I never go to an "ide" or anything like that. I literally just say their names. It doesn't matter how many of them that there are. I just say their names. So in this case, there are 2 nitrates here, but I just say nitrate because I'm expecting you to understand that the nitrates have a -1 charge on them. And if my iron has a +2 charge on them, then I'm going to need 2 nitrates. Okay. So let's go. Let me copy. And then we'll delete all of that. All right. So how do I get a name out of this formula? Well, this is calcium. It's only got 1 oxidation state, so I don't have to use a Roman numeral with it. So that means I'm just going to say calcium. And then what's it connected to? Carbonate. And I said earlier that I never change the name of the polyatomic ions or give any number indication with it. So I just say calcium carbonate. That's chalk. Okay, so the next one. I've got a sodium. Sodium is a group 1 metal, so its oxidation state doesn't say change, so I don't need a Roman numeral with it. So I'll just say sodium. And then I've got phosphate. That's that polyatomic ion. Okay. The next one is an iron, and that does have a variable oxidation state. So I need to look at the nitrates, and the nitrates have a -1 charge, but there are 2 of them. So that means it's got a -2 overall. So then the iron must be a +2. So it'll be it'll be iron 2 nitrates. So again, the 2 doesn't mean 2 irons. It means the irons have a +2 charge on them. And then the next one here, it's just 2 polyatomic ions. So I could just say their names. Ammonium chlorate. And that's it. So how do I go backwards? How do I go from the name to the what is going on with this? There we go. How do I go from the name to the formula? All right, so I'm looking at this and I see calcium. So calcium has a +2 charge. I know that because it's in column 2. And carbonate has a -2 charge. I know that because I've got all of my polyatomic ions memorized. So then I just put down the formula, CaCO3. I only need 1 of each, and I'm good to go. What about the next one? All right, well, sodium is in group 1, so it's got a +1 charge, and my phosphate, that's a -3 charge. So then I'm going to need 3 of my +1 sodiums to go with my 1 -3 phosphate. And sodium phosphate is something that you use if you're stripping a floor of wax. So we did a lot of that on the ship, or in the Navy. Not a lot of fun. Okay, so in this case, I'm being told that the iron's charge is a +2. Okay, and then I know my nitrate's charge is -1. So I'm going to write Fe, and then I know that my nitrates are a -1, so that means I'm going to need 2 of them. So that's how I write it. Parentheses around my polyatomic ion with a 2 on the outside is telling me I've got 2 of everything that's inside of that polyatomic, or everything inside those parentheses. And then the last one The ammonium has a charge of +1 and the chlorate has a charge of -1. So I just need one of each. So NH4 and ClO3 and I'm good to go. And that's it for my ionic nomenclature. I wish the ionic nomenclature was as easy as the covalent nomenclature, but I'm sorry, it's not. So with the covalent nomenclature, you do need to have these prefixes memorized, and I'm assuming you know almost all of them. The ones I think people don't usually know are non and hepta, but mono, we all know that's 1, di is 2, and tri is 3. Maybe tetra, although tetris is a 4-sided figure, so that's 4. Tetrahedral, so you probably learned that in geometry in high school. Penta, maybe you remember that from the Pentagon or the building that's where we house the Department of Defense. Hex is 6. Hepta is 7. Oct is 8. So octagon or octane for gasoline. And then non, so that's just 9. So nonane would be a molecule with 9 carbons in it. And dec, we know that one as being 10. All right, so it's pretty easy. There's, for the nomenclatures for this, well, I already have those missing. So carbon monoxide. So the way this works is the first element, each of the substances is going to get a prefix like di or tetra or something like that based off of how many of them that are there. Unless the first atom is by itself, and then the second atom in the substance will always have its name changed to I. So carbon monoxide is 1 carbon and 1 oxygen, and that's the whole thing. So what we do not say with this is mono carbon dioxide. We'll only ever use the prefix mono if the second thing is by itself. Another example would be like N2O. So this would be di nitrogen monoxide. Or CO2 is not monocarbon dioxide, it's just carbon dioxide. So again, we are using that IDE ending. That is happening every single time. But again, this is a lot easier. So phosphorus pentachloride, since there's nothing written in front of the phosphorus, there's just 1 phosphorus there. And penta means 5. So that means I've got chlorines and I've got 5 of them. Okay. So dinitrogen pentoxide. So that means I've got 2 nitrogens and I've got 5 oxygens. And that's it. Sulfur, nothing written in front of the sulfur. So this is just S. And then I've got fluorines and I've got a hex of fluorines, which is 6 fluorines. That's it. So if I want to go the other direction with this, so I've got CO and PCl5 and N2O5, 2, and then I've got SF6. Okay, so let me bag all this stuff, delete you, drag you over here. All right, so I'm looking at this and I'm seeing, okay, so these are non-metals. I know that because there are no metals up here and no polyatomic ions. So this carbon is by itself, so I'm just going to say carbon. The oxygen is by itself, so that means I need to say 1 oxygen. So I know that that doesn't really look right, although you can write it like that. But what most people do when there are 2 vowels right next to each other is they just get rid of 1. So instead of monoxide, monoxide just comes out quickly. Okay, so the next one, the phosphorus is first and it's by itself. So I just write down phosphorus, and then I see 5 chlorines. So then I have to identify that as penta and then oxide. All right, so next one, 2 nitrogens. So I say that by saying di nitrogen and then penta oxide. You know what? I'm sorry. I made a mistake here. I was looking at the next one. Pentafluoride. That's the problem with having a straight online class. I don't have any students there pointing out my mistakes. And so then the last one here, a sulfur by itself. So that's just sulfur. And then 6 fluorines is hexafluoride. That's it. So again, the covalent nomenclature is much easier than the ionics. So lastly, we're going to do some acid nomenclature, which has some ionic nomenclature, specifically polyatomic ion nomenclature associated with it. So again, we're going to name these when we see a compound that starts with an H, or anything that starts with an H, we're going to identify as an acid. There's 2 things that we need to identify associated with their work. We need to point something out. If there's oxygen in it or not. If it contains no oxygen, then we name it like this. If it contains oxygen, then we have to name it a little more difficultly. So if it's got no oxygen in it, I'm going to start off my phrase with hydro. And then, so there's no oxygen here. So this is hydro and then chloric acid. So I'm always going to end with this acid part, the word acid with any of these. So HCl is hydrochloric acid. HBr is hydrobromic acid. I'm saying hydro because there isn't any oxygen present. So if I see something like, I'll do that here in a second. So if you see hydro, like hydrochloric acid is stomach acid, you know that that acid is composed of hydrogens and something else, but there aren't any oxygens in it. Okay, so what about if there's oxygen? The way the oxygen compounds get turned into acids is the polyatomic ion has H's added to it until it becomes an acid. So SO4 with a minus charge was sulfate. If I put 2 H's on there, each of the H's come as a plus, and so then that cancels out. And so now what I've done is I've created a neutral molecule that is now called sulfuric acid. So how do I get sulfuric acid out of that? So I have to identify the polyatomic ion and its suffix. And if its suffix ended in an 8, then I change it to an ic. So that's where we are right here. I'm changing this from an 8 to an ic. If it ended in an ite, then I'm going to change that to an us. Okay, so if I've got NO3 and NO2, this is nitrate and nitrite. If I put an H on here to cancel out the charge, this is, and this is, so nitric acid and nitrous acid. What is missing from this? Hydro. I don't use the hydro prefix because there are oxygens present. So again, this one got to be called ic acid because it came from nitrate. And this one became us acid because this came from nitrite. So here's another example. Why is sulfuric acid named as it is? Because it used to be sulfate. And so I take that 8 and I convert it into ic and it becomes sulfuric acid. Phosphoric acid is phosphoric acid because it used to be sulfate and 8s turn into ics. This is sulfurous acid because this is SO3 is sulfite. So ites become us's. So I always put those together. I said 8-ic real fast, like something got eaten. And that's how I associated ic and 8s with each other. And us's and ites sounded, I had like an ite-us. So it sounded like a disease, ite-us. So that's how I knew those went together. So if I recognize that that was the polyatomic ion sulfite, then I know ite-us. So I changed that to sulfurous acid. And that's it. That's all we have for nomenclature stuff. So give you lots of opportunities to write down nomenclature names and formulas from names and whatnot in homework. Okay, that does it for chapter 2.